Hey guys, sorry that this video is in this kind of circumstances, but I want to do my best to help you be prepared for the material that I'm asking you to do some homework on. That's the purpose of this video, is to provide you the necessary instruction you need to be successful with lesson 1.5. We're going to be looking at functions in this lesson, but before we do that, I've got a couple question bell ringer that just provide you some extra practice. I encourage anytime that I go over an example, with having the use of technology here, encourage you to pause the video and try the problems on your own and then hit play. So I'm not going to create a lot of wait time to make the video any longer. So please feel free to pause the video anytime we're doing examples and then try them yourselves and then hit play, and that's a great way to check for understanding. So let's get after it. So with this bell ringer, there are two questions. One, finding all the real values of x such that f of x equals 0, and then find the domain of the function given there on the second one. So let's go ahead and switch over. I'm going to switch over to a .cam and we'll work out this problem, this first one where we're finding all real values x such that f of x equals 0. So if we're told that f of x equals 0, well, here's f of x. Okay, so that's going to be 0. So 0 equals 3x minus 4 all divided by 5. Anytime we have a rational expression equal to 0, we know, or a fraction equal to 0, we know that the numerator has to be 0. I don't get 0 out as out of a fraction unless it's 0 divided by something. So from this, we can take away that 3x minus 4 has to be what equals 0. And then through solving this simple algebra equation, we're going to add 4, divide 3. I'll just do that all at once. Add 4, divide 3, and we get x equals 4/3. Notice 4/3 is indeed a real value, and so that is the answer. And of course, we could check if we wanted to take the time, substitute 4/3 in for x, and see that we get f of x equaling 0. Second question, find the domain of the function. So keep in mind, the domain of a function is the values of x, the set of values of x that exist in this function. So anytime that we're working with, again, rational functions, where we have a denominator that has our independent variable here, we need to think about, well, what can x not be? So in this first fraction, 1 over x, x clearly cannot be 0, right? And in the second fraction, we know that x cannot be what? Should be saying -2. Okay? X can be anything, any other real number we want it to be. I can take 1 divided 4, I can take 1 divided by pi, I can take 1 divided by 6.38157, I'm just making up some numbers. And likewise, I can take 3 divide any of those. I just cannot take 3 divide -2 plus 2 because that turns that into 0. So those are our two values that are excluded from our domain. So the assumption is, if I just write x cannot equal these, that x can be all of the others. Okay? So hopefully that serves as a good little refresher for things that we did in the previous lesson 1.4. All right. So let's get back to our lesson and our new material. Okay? This lesson is titled Analyzing Graphs of Functions. All right? There's quite a bit that we're going to discuss here in this lesson, so stay tuned for that. Here's our objectives. We've got 5 of them. We're going to use the vertical line test for functions, something that you should be aware of already. We've talked actually a decent amount in previous classes about this, so that shouldn't be necessarily new. Finding the zeros of functions, we actually already did that this morning in the bell ringer, but it's just another terminology, another vocabulary for something that you've already done. Determining intervals on which functions are increasing or decreasing, and then determining relative max and relative min values. Determining the average rate of change of a function. And lastly, identifying even and odd functions. New vocabulary because we're describing functions, but we've actually already done that as well. So those are our goals for the day, for the lesson. So hopefully as you follow along, you'll be able to see that we're addressing each of these things. All right, so starting with the graph of a function. Again, we've studied functions from an algebraic point of view, In this section, you'll study functions from a graphical perspective. So very much a heavy graphical perspective here for this lesson. Okay, the graph of a function is just a collection of all the ordered pairs that satisfy the equation. All right. It says such that x is in the domain of the function, which if x is not in the domain of the function, you won't have an ordered pair for that value. So still the collection of the ordered pairs for the function. So here's the graph of a function. We know that this is a function because our definition that we looked at, for every x there will be exactly one y. There's no spot on this function where one x has two y's. If that were the case, they'd be stacked on top of each other, which is where that vertical line test that we'll talk about in a moment comes in. So this question is asking again from a graphical perspective. Here's a graph. Can we identify the domain, the function values, and then the range? Okay. So let's take a look at that together. Again, I'll go ahead and switch on over to the DotCam. Great opportunity for you once again to pause the video and try this on your own. It's about zooming in here a little bit more to make it a little bigger. So we're asked for the domain of the function. Again, when we talk about that term domain, we're thinking about the values of x that make sense in this function, the values of the input. Okay, so so I'm trying to answer this, the domain of the function, this is our function graphed, and these are x values on this x-axis. I'm looking for where do the x values live? Do any of my x values live down here? Do any of those -3, -4, -5 over here have homes or places on the graph? No, there's no spot for -3. What about -2? No. -1? Sure, yeah, -1 has an output of 1. -1 has a home. So that's our first, from a left to right perspective, that's our first x value that lives on this graph. Does 0? Yes. Does 1? Yes. Does 2? Yes. Does 3? Yes. Does 4? Yes. Does 5? And you notice there's an open circle here. Keep in mind when we graphed inequalities on a number line, you've probably seen that open circle versus filled in circle notation before. So this is saying the input x equaling 5 does not actually have a place. 4.99999, it does, it goes right on up to this point, but it doesn't actually have a point at 5. So for that reason, we can say that 5 is actually not in our domain, okay? So we started at -1, and we saw this continuous curve all the way to 5, but not including 5. So this is a great place to use integral notation. So the domain of f is at -1 to 5. We said -1 is included, so we use one of those square brackets, and 5 is not, and so we use a parenthesis. So that would be our domain of that function. Second, f of -1. So this means what's the function value at an input of -1? So in other words, what's the y value or the output is what function values are looking for. So at -1 as an input, what's my output? My function values. So our y values, or our f of x's, okay, that's 1. So this is 1, so let me go right here and I'll say f of -1 is 1. Well, then they also ask for what's f of 2. So what's the function value at an input of 2? Well, the input, or the x value of 2, let's find 2 on the graph. There's my x of 2. Let's find it on the actual graph. Oh, it's right there. And that says that it has an output, a function value, a y value of -3. So f of 2 is -3. Okay. Lastly, range. Okay, so just like domain is the set of inputs that the function takes on, the range is a set of outputs that the function takes on as well. So what are the outputs? So it's kind of like, I sometimes will say in some classes, after you've found domain, go ahead and just shift your head 90 degrees, because our domain is this from here, roughly. Where was our domain? But our range is now scanning the y-axis for which y values get used in this function. And it looks like the highest y value used is up here at 3. And then every y value is used all the way down to this one at -3. right? Now some y values are used more than once. This one right here at 2 as a spot here and here. This one here at 1 is a spot 3 times, 1, 2, and once again over here somewhere. So, but that's okay. But the range overall would be this right here. And so what outputs do we go between here? Looks like our smallest one was -3. So we can say -3, 2. The highest one of 3. Now the question is, do we include each of these? So you got to look and see when -3 is used, is that an actual included value on the graph? Yes, it's a filled in dot right there. And then when 3 is utilized, is that an included value? Yes. So we would have a square bracket on both of those. Okay? So that's that first example dealing with domain and range and function values. All right, let's head back to the lesson here. You'll find that we were accurate there. Use of dots, open or closed, at the extreme left and right points of the graph indicates the graph does not extend beyond these points. So this is an important feature for you to realize. In our book, if they don't want the graph to extend further on, they're going to put visible dots as endpoints to a function. Otherwise, you'll just kind of see the graph continue to trail off. And that would be an indication that the graph continues as opposed to stops, okay? So be watching for that. I don't believe our book has the habit of putting arrows on the end, something that you or I might do on a paper to denote that the graph of the function continues. So be watching for that, okay? And it does say here, if no such dots are shown, assume, so they're telling us it's safe to assume here that the graph extends beyond those points. Again, provided the hypothesis of that conditional statement is that no dots are shown. Okay, so this is leading us into the vertical line test. Remember again, the definition of a function is that for every single x, there is exactly one y. So what would violate that? What would violate that would be where there's an x that has more than one y. Well, if you think about what does that look like visually, again, we're here studying today the graph of a function, very much a visual concept. What would violate that would be a spot where there's a point, and then a point on the function or on the graph, I shouldn't say function, and then a point on the graph directly above it would be a violation, because those two, if they're stacked directly above each other, would be an x value that has 2 or more y values. So that's why the vertical line test exists, as a test to determine whether something is a function or not. If you can pass a vertical line across the graph of something and it never intersects the graph at more than one spot, that's a function. That, what we would say, passes the vertical line test and is a function. Okay, so that's what we're getting at here. I think this is saying pretty much exactly what I just said. Okay. So here is formally that vertical line test. It says a set of points in a coordinate plane is the graph of y as a function of x, if and only if there's that biconditional statement or definition that you should have learned about in your geometry days. If and only if what? No vertical line intersects the graph at more than one point. Okay, so that's why this ends up being a test for whether it's a function or not. Okay. All right, zeros of a function. Okay, zeros of a function is just a term that is synonymous with the x-intercepts. It's synonymous with that bell ringer question that we did first today that said, find all real values x such that f of x equals 0. Ultimately, without introducing the vocabulary, what you were finding right there was the zeros of that function. Now notice that zeros is plural. A function can have many zeros. They can actually have infinite zeros. As we will get to studying some trigonometric functions, we'll see that it's common that a function would have infinite zeros. It's also possible that functions have no zeros. If you think about the parent quadratic function, x squared, I'm sure you're pretty familiar with that function by now. If you were to take that function and just shift it up, it never touches the x-axis. So it has no x-intercepts. it has no zeros, in other words. So know that it's not a requirement for a function to have a certain number of zeros. It can have none, it can have one. Again, that parent function x squared, that would be an example of it having 1 0 only, because the graph just comes down and touches the x-axis, okay? So by definition, what is a zero? A zero of a function is or are the x values for which the function output is 0. Okay? Hence why we call it a zero of a function. And mathematicians aren't always the most creative people. They just tend to use common sense terminology. Okay? But notice it's the same thing as an x-intercept. All right, so let's practice it. Just like we did in the bell ringer, let's try it with these 3 functions that are given. We're going to find the zeros of each of these functions. So once again, great opportunity for you to pause the video and try this from home. I'm going to switch over to the dot cam and we're going to do it together. So this first function says find the zeros of f of x equals 3x squared plus x minus 10. So first off, when you see find the zeros of a function, you need to be thinking, well, that's when f of x equals 0. So I'm going to start by replacing f of x with 0. And as I've asked in the past, anytime you have an equation set equal to 0, one of your first thoughts as a strategy for how to solve it is your favorite 6-letter F word, and that is factor. Okay, so we'll go ahead and factor this expression. This is an expression that has a prime leading coefficient of 3. So from your factoring practice in Algebra 1, hopefully you remember that then this is going to be a 3x and an x. And then we've got our factors of 10, 10 and 1, 5 and 2. We want the difference of them to be a positive 1. So I think what we need to do here then is we need to make this a 2, and we want that to be positive so that I end up with this product on the outers being 6x, and we want this one to be negative 5, so the product of the inners is negative 5x. They combine to make 1x, and the product of the last is that negative 10. So that is exactly how it factors. And now to finish solving, we set each of those zeros each of those factors equal to 0. And solve for our zeros. So we're solving 3x minus 5 equals 0 and x plus 2 equals 0. And at this stage in this class, I'm not necessarily expecting I see the steps of work to solve for each of those, because they're 1 or 2 pretty easy steps. Subtract your 2, so you know that x equals negative 2. And then add 5, divide 3, you should get 5/3 as your other one. So we have 2 zeros.
Good morning, everybody. We will have a full staff meeting in 10 minutes in the auditorium. Sorry for the inconvenience.
So next, sorry, I'm getting an announcement over my phone. Next, we're going to go ahead and find the zeros of this function. So we're going to set that equal to 0 and solve. So as I set that equal to 0, I get 0 equals the square root of 10 minus x squared. We need to go about solving this equation. Okay, so a couple ways of doing this. First off, I would encourage you to think at this spot, the square root of what equals 0? Does the square root of 5 ever equal 0? The square root of 10? The square root of negative 3? No, the square root of only one number equals 0, and that's 0. So that means then that 10 minus x squared has to be 0. Well, by manipulating this equation, you know that x squared then has to be 10. And then by square rooting, we learn that x must equal plus or minus, right? Anytime you yourself are the one to put the square root on, you must include the plus minus. X equals plus or minus 10, okay? Because it doesn't matter if it's negative root 10, as soon as I square that in there, as I substitute back in to check, I get 10. And so then 10 minus 10, 0, the square root of 0, 0, or if that's a positive, they both check out, okay? So those are our 2 zeros of that function. Lastly, just like our bell ringer question, I need to find the 0 of h of t. Again, I'm not doing h of 0, I'm asking what's the 0 of h of t. So 0 equals 2t minus 3 all over t plus 5. Again, this is a fraction. In order for us to get 0 out of a fraction, it only works when the numerator is equal to 0. So from this, I know that 2t minus 3 equals 0. Go ahead and add your 3, divide by 2. You learn that t equals 3/2. Okay? So that's how you find the zeros of a function. Again, one of the beautiful things about being able to have this lesson video is if something doesn't quite make sense, or Mr. Breen speaks too fast or something, you can pause the video and you can rewind it and relook at it again. Okay? But I think you'll find as we click through these that these are the solutions that we got together. They show you the visual. Again, this is a lesson studying the graph of functions. So here's the graph of that first function we looked at. And again, just re-emphasizing that the zero of a function is an x-intercept. And so notice that this quadratic has 2 x-intercepts, so 2 zeros. Okay, and the second one, we got x equals plus or minus 10. Sure enough, if you were to graph that function, it's a semicircle, and notice that it has 2 x-intercepts. Those are our zeros. And lastly, this rational function, okay, it has the 1, 0 at t equals 3/2 like we found. All right, next I want to talk about this concept of increasing and decreasing functions. This I'll be, right from the start, I'm going to be pretty transparent with you that many different textbooks will actually talk about this slightly differently. And so I'm going to teach you the way that our textbook specifically addresses this, but I will also at least fill you in, make you aware of the difference with other textbooks. And actually the main reason I want to do this is at a calculus level, we define increasing and decreasing functions slightly differently. Okay? So the more you know about a graph of a function, the more you know about the function itself. So here is a function. It says as you move from left to right, this graph is falling from x equaling -2 to x equaling 0, and then it's constant from 0 to 2, and it rises from 2 to 4. Okay, so always they italicize there from left to right. That's how we want to read the graph. The second thing, and this is one of the most important key things I need you to hear clearly, when we describe a function as increasing, decreasing, or constant, it's always on, here it is, it's always on an interval of x values. I can't tell you the number of times through the years that students will say, oh, it's decreasing from 4 to 1. They're looking at the y values, 4 to 1. No. It's decreasing on this interval from -2 to 0. It's constant on this interval from 0 to 2. It's increasing on this interval from 2 to 4. It's always on an interval of x values, okay? Now, our book takes the stance that it cannot be decreasing, constant, or increasing on any specific point. A point in and of itself is not increasing, decreasing, or constant, which makes some sense. You need to have points around it. I can't say if I'm going 2 miles an hour, if I all of a sudden am just going 2 miles an hour, that instant, I can't necessarily say whether my speed is increasing or decreasing. It is all relative to what is around it. Okay, so this is going to come into play because when we use interval notation here to identify decreasing, increasing, constant intervals, we are never, hear this clearly, going to use square brackets. We will always use parentheses when noting those intervals. Okay? Here's just the technical jargon of what does it mean for a function to be increasing, decreasing, or constant. It just says, you know, increasing. Functions increasing on an interval. If any x1, x2 in that interval, the x1's left of the x2, that's what that means if x1's less than x2. That implies that the output value, the function or y value for x1 is smaller than the function value or output for x2. That would make sense for the function to increase on that interval if that applies. Okay, and then kind of coincidingly, the other definition there for decreasing and constant as well. Don't get too hung up on it. More than anything, again, this lesson is on the graph of a function. So you're going to be reading graphs and identifying increasing, decreasing, and constant. Okay? So example 4 says, use these graphs to describe the increasing or decreasing behavior of each function. Okay, so let me switch on over to the .can one more time for some examples on that. Okay, so here just copied everything over. Identify intervals where the function is increasing, decreasing, and constant. And I'm going to zoom in here a little bit. So, graph from part A, let's talk about increasing. Where is this function increasing? Well, notice this function has arrows on the end of it, so it continues forever, and it's showing the entire trend of this graph. What is, I read from left to right, what is, and I just trace over this. What is my pen doing? Is it increasing? Is it decreasing? Is it ever constant? Hopefully you would agree that this increases on the entire domain. So we would say it's increasing from negative infinity to infinity. Okay, notice again the parentheses. Well, we would use parentheses anyways on interval notation when we're utilizing negative infinity and infinity, but we're going to use parentheses here because we will always, on every single one of these intervals, we will use parentheses. Well, if it's increasing on this entire domain, then it should be trivial to say that it's never decreasing and constant never. Okay? Even if you were to zoom in, you might think, oh, it's constant right here near the origin. No, if you were to take a look at this function and zoom in, you'd see that it's always increasing. Okay? All right, maybe a little bit more fun of a function here. Again, we know that each of these are functions. We didn't have an example of it, but let me just make sure it's explicitly clear here on what that vertical line test is meaning. If I pass a vertical line over this function, never does my vertical line intersect the graph at more than one spot. Okay? So increasing on this one, where is it increasing? Again, we're thinking as we move from left to right. If I were tracing this, oh, I'm increasing right now. All of a sudden no longer. Oh, so what was that interval? Arrow. So we're saying from negative infinity to what x value? When do I stop increasing? At negative 1. And notice a parenthesis always. Decreasing. Where is it going down? So I started saying it's going down right here. When do I stop going down? Oh, I stopped going down right there. So what are those x values? From negative 1 to 1. It was decreasing. Oh, but then what does the graph do all of a sudden? It starts increasing again. So I could say union if I want, or I could just put a comma in between there, but union, when else is it increasing? From 1 to when? Keeps going. Oh, I get the idea. To infinity. Okay? As I keep going further to the right, I am going to keep increasing. Okay? And here, lastly, one last example, increasing. So so where is this function increasing? As you read it left to right. Oh, I'm out here. This looks like my pen is going up. Okay, but then I get to this spot and I stop and I move horizontally. That's constant. So here's my increasing. How do I describe that interval? Negative infinity, because my arrow on the graph, all the way to what x value? 0. Then it's, well, I've been always doing them in this order. What does the graph do next? It starts going constant, just horizontal. Okay, well, what are the x values? Starting at 0 and moving constant to 2. Decreasing thereon forever. So where is that? From 2 to positive infinity, it is decreasing. Okay? So again, hopefully that makes sense as we talked about the increasing, decreasing, and constant behavior of functions. Again, I think you'll see that our answers match the answers here. So there were those two intervals on part B where it was increasing, and then the one interval for decreasing, increasing on the entire domain on A, and then we have an interval for each on C. Okay. Yeah, it says, to help decide whether a function is increasing, decreasing, or constant on an interval, you could just evaluate a few function values, and that would help. Okay, it says, however, calculus is needed to determine for certain all intervals for which a function is increasing, decreasing, or constant, and that's true.